Please.
Thank you very much. So, thank you organizers, Katja Krupchuk and Knut Solna, and maybe I forgot some of the organizers. So thank you very much for the occasion to speak here. So I'm going to speak about the D-bar system, which appears in the Davies-Stewartson equation and other similar contexts. And this is a joint work with Christian Klein and Nicolas Stoylov. And we recently put a preprint on archive. So what happened now? I need to, next. I'm afraid of touching this. I can't change the page. Oh no, this is terrible. Because it goes, it changes automatically. Well, this is the first, anyway, so far so good. So it comes from the questions about the Davies-Stewartson equation. So my collaborators, they know the background. So my own contribution is to work on a particular D-bar system with methods of complex analysis and oscillatory integrals. So the system is the system 1 here. So it's a system with two unknown functions on C. One satisfying D bar phi 1 equal to a factor times phi 2, and the other equation is D of phi 2 equal to a similar factor times phi 1. And the conditions at infinity are that phi 1 should tend to 1 near infinity and phi 2 should tend to 0 near infinity. And actually we will not work with in soup norms, so this is to be interpreted in the sense of L2 spaces with weights. And K is a complex parameter, so ideally one would like to solve this system for all complex values of K. And the motivations of my collaborators is that if you want to do this for all K, then it will be quite hard to do this numerically when K becomes large. So therefore one would like to solve this for, say numerically for K in a bounded region, and then for large values of K, try some asymptotic method so you can write down the solution more or less explicitly. So Q is potentially could have compact support or decay fast enough at infinity. D is the ordinary complex differentiation operator, and D bar is the dx minus 1 over I dy. And so there is the focusing case, which is when sigma is equal to 1, this coefficient here, or, the defocusing case, and sigma equal to minus 1 is the focusing case. Actually, for our analysis, since we will work only in the case when K is large, it doesn't matter if sigma is equal to 1 or minus 1. So there are differences, important differences here for K in a bounded region, but not for large K. How can I change? I don't understand why I can't change the. I don't know. So it's very strange. It doesn't. So there have been many works on these systems. So here are some references. It's Beals-Kaufman, Sung, Brown and Ullman, Brown, Peter Perry, Nachman, Regev, and Tartaro. And our work is focused on the case where K is large. So the plan of the talk is that I will first review quickly how you solve the d-bar, how you invert the d-bar operator using the Hermandes method with Kalman weights. And then I will show how you can solve the system if you have some regularity assumptions on Q and some decay assumptions, then you can solve this with the convergent Neumann series. So the local regularity should be that Q is of class HS for S strictly larger than 1. And our estimates, we don't gain, we restrict the S to be smaller than or equal to 2 because the estimates that I will write down are not necessarily valid for higher values of S. And the other case we're interested in is when Q is the characteristic function of a strictly convex domain with smooth boundary. Actually, for the most detailed results, we will assume the boundary to be analytic, but probably that assumption can be relaxed. Also, we did not work it out, but inside this strictly convex set, you could have poles which are also strictly convex. You can remove strictly convex subsets of omega. And then I will speak a little about the leading corrections to the so the phi 1, for instance, will be of the form 1 plus a correction term, and phi 2 will be of the form 0 plus a correction term, and I will discuss the structure of these correction terms in the case when Q is the characteristic function. And then at the end, some numerical illustrations. I'm really bad at let's try to. No, I cannot. What happened now? I cannot change the page. Is there something strange? So it's, let me. Oh, no, sorry. Focusing. What happened now?
Just press on the slides. Press on the slides.
I cannot full. How do I get full screen? Oh, now back. So I have to put. Oh no, here I can. Oh no, that's terrible. No, okay. Oh, here I can change the pages. Okay. So let me first discuss, just recall how you treat D-bar problems with the Hermander-Karleman method. Well, in our situation. So the idea is that you conjugate your operator with some weight. In our case, we will take a polynomial weight. So I have the Japanese bracket Z. It's basically 1 plus norm of Z. And I conjugated the D-bar operator with the bracket Z to the power epsilon. And you look at the adjoint operator, which is, so the adjoint of this guy here comes here, the adjoint of this one comes here, and the adjoint of this one comes here. And more explicitly, I have these formulas for it. So the conjugation affects only the zeroed term in the operator. And then you look at the commutator, and the commutator here is epsilon times dd bar capital phi, where phi is the logarithm of bracket z squared. And you compute that bracket, and you see that it's bracket z to the power minus 4. So it's small at infinity, but it's sufficiently positive so that you can do things with this. And then finally you use the simple fact that p epsilon star is, in the operator sense, is larger than or equal to the commutator. So I subtract a term here, then I can only decrease the operator. And this is what I just wrote on the preceding line. So this, so in the Hermander method, this is used is usually p epsilon star p epsilon that is used, and that gives you, well, I will not, I will just, let me just continue here. I'll take the next. So this implies that you have a nice a priori estimate for p epsilon star. Huh? So what's here, this is written as you can, from this you can estimate the L2 norm of p epsilon star from below by some negative power of z times u, huh? In L2 sense. And once you have an a priori estimate for p epsilon star, then you can get an existence result for p epsilon. And then you can, now p epsilon is just a conjugation of the d bar. So this gives you, so this gives you an existence result for d bar. Huh? So what you get is the following proposition. So we let epsilon be positive. Then if I take v in L2, v of the form L2 times the bracket of z to the power epsilon minus 2, then there exists a u in the space bracket z to the power epsilon times L2, solving the inhomogeneous equation, and we have an a priori estimate. So you lose 2 powers of bracket z when you do this. Huh? And if I restrict my range epsilon to strictly between 0 and larger than 0 and less than or equal to 1, then I get a unique solution, and this solution is given by the standard formula for with the fundamental solution, the classical fundamental solution of the d-bar operator. So LDW is the Lebesgue measure. And I will use that this Lebesgue measure can be viewed as a 2 form, dW bar wedge dW over 2I. Now, before looking at the system, so we see that when we solve the d-bar problem, if I want to solve the d-bar problem, I will also use a semi-classical point of view. So h will be a small parameter. Actually, it will be equal to 1 over the norm of k. And when I solve this equation, then I will lose 2 powers of bracket of z, and then I will also lose a power of h, because I have this factor h. I have to divide by h. Huh? But if I look in the phase space, this trouble comes from the 0 section, because the symbol of our operator, the symbol of d bar is written here. It's psi plus I eta. It vanishes near 0. So if I multiply by 1 minus chi of psi, then I cut away the set where the symbol vanishes. So if I so I do this on the Fourier transform. So on the function sides, this is to apply a very simple pseudo differential operator, 1 minus chi of ht, and chi is a cutoff function which is equal to 1 near 0. Then I get this equation, and then it's much better because on the support of 1 minus chi of psi eta, my symbol here is non-vanishing, so I have an elliptic equation. And therefore, this leads to a much better situation, namely you don't lose any power of bracket of z, and you don't lose the 1 over, you don't have to put the 1 over h either. Huh? So you have a great improvement if you just avoid the 0 section. So now I will discuss our d-bar system. So I will take Q in the space HS times dot Z to the power, dot bracket of Z to the power minus 2. In our system, we had this complex parameter K, which I write as Kx plus I Ky. And then you can, so then this function here is is oscillatory. And I can write it as H, if I introduce H to be 1 over norm of K, then this takes the form I over H, that is I times norm of K, times the R2 scalar product between the point XY and the vector omega. And the vector omega is what is written here. So it's a vector of norm 2. And then in our original problem, there was the multiplication by exponential functions. So now this multiplication, I now write it in this form. And I give a name to this multiplication, I call it tau omega hat. So tau omega hat means translation with omega on the H Fourier transform side. So I will not define H Fourier transform is just the H Fourier transform of a function u at the point psi is just the ordinary Fourier transform at the point psi over H. So if, with this notation, the system we are interested in takes this form here. And again, I want to solve this with phi 1 tending to 1 at infinity and phi 2 tending to 0 at infinity. So we first take phi 1, we take an approximate solution. We just take phi 1 equal to 1 and phi 2 equal to 0. I call this phi 1 0 and phi 2 0. I plug it into the equation. And then what I get is not a solution of this problem. For the first equation is all right, but in the second equation, I get an error, which is just this term here. But in this, and then so if I look at the powers of phi 1 0 is 1, so this behaves like bracket Z to the power minus 2, basically, because of Q here, which has that behavior. I should maybe mention that since S is larger than 1, to be in this space implies that I'm in the same, that I'm in L infinity times this factor here. So, okay. So this means that we run into an inhomogeneous system that we have to solve. So let's write down a general inhomogeneous system. So in our situation, we have psi 1 equal to 0 and psi 2 equal to a special expression that we had on the previous slide. And we want to solve this for psi 1 and psi 2 in this weighted L2 space for some fixed epsilon between 0, strictly above 0 and smaller than equal to 1. So as I said, for Q is O of bracket of Z to power minus 2. So I will do an iteration procedure. So I introduce the inverses of this operator here and this operator here. So the inverse of H d bar, I call it E. It's the solution of this equation, and F of V is the solution of the corresponding complex conjugate equation. So when V is in this space, then as we have seen, U and U tilde will be in this space. For the equation D, we have the same results as for the D bar, because it's just a complex conjugate. So now I invert this operator to my, and then I get a new system which takes this form 1 minus Ka phi 1 phi 2 equal to then I have to put an E here and F here. No? And the operator K is now it's 0 on the diagonal, and off the diagonal I have this thing here with composed with E to the left, and here, and then I have this thing here composed with F to the left. Huh? So I will, by definition, this operator I call it A, and this operator, and this I call it B. Huh? Now, using our propositions about solving the D-bar problem, we can see that this takes us from a dot bracket of z to the power epsilon L2 into itself, huh? Because when I multiply here, I have an improvement, and then this is a unitary operator, and then I apply E, so I come back. So here I come to dot bracket of z to the power epsilon minus 2, and then I apply E, and I'm back in bracket of z to the power epsilon L2. And this is O of 1. So this is a bounded, uniformly bounded operator when H tends to 0. So as I said here, sorry, here's this should be an epsilon, not an epsilon 0. But this is not enough to invert 1 minus k, unless we assume q to be small. So the observation now is that if I, instead of looking at k, look at k squared, then this k squared takes this form, and this is actually of smaller norm. Huh? So I want to explain. So the proposition now, and there is a similar result in Perry's paper. The proposition says that k squared behaves like O of h to the power s minus 1 in my space. And I recall that s is strictly larger than 1, so I gain some positive power of h here. So therefore, when h is small enough, that is when norm of k is large enough, I can invert 1 minus k squared. And if I can invert 1 minus k squared, I can also invert 1 minus k, because this is a way of writing the inverse of 1 minus k. And this inverse, I can spell out what it looks like in matrix form. It's written here. It's 1 minus AB inverse and 1 minus BA inverse on the diagonal, and then times a matrix which has identity on the diagonal, and A and B off the diagonal. So I explain the proof quickly the proof of this. Huh? So I look at k squared. The k squared you compute, it's this matrix here. And now you recall the definition of A and B. So A is this operator here multiplied by h over 2. And B is this operator multiplied by h over 2. So I get this expression here. And now I split this into 3 terms by putting in the cutoff functions on the H Fourier transform side. So here is again the product. This is AB again, but here I have an additional factor. So I want 1 minus chi. So chi W is just a quantization of chi. It means on the Fourier transform side, I multiply by chi of H times psi. So I just put this factor. So if I put this factor, then I need a correction. So I need a similar expression with chi instead. So it should. So then I could take this, except that I threw in another chi here, and to correct for that, I need another term with 1 minus chi here. Huh? So therefore, in this decomposition, I managed to put the factor 1 minus chi coming with the f in this term, and here I get the 1 minus chi coming with the e in this term. But then I have a third term where I have chi at two places. Huh? So now, there was this observation that if I avoid the zero section, the inverse operators of the d bar and d are much better. So here I managed to have 1 minus chi here. So this is, so E and F are over 1 over H. But because of this factor, this is over 1. So I gain one factor of H. So this is O of H. Similarly here, I gain a factor 1 over H here. So this is also O of H. And then we have to discuss this last term. And here I will not go into the details. What you do here is that you look at this expression here, sitting in the middle here. So a priori, this is only over 1 because E and F are both over 1 over H. Huh? But when I look closer at this, what happens here? If Q is smooth enough, here I may make a cutoff near frequency 0. Then I multiply by Q. So if Q is smooth, it's still, the frequencies are still mainly concentrated near 0. And then I have this phase-space translation, which, so if I go up to here, if I apply this to some function, then I expect to be close to the frequency minus omega. But then this cutoff takes away that part, huh? Because chi is supposed to have support in a small neighborhood and omega is of norm 2. And therefore I gain, so this I get O of H to the power S minus 1. Huh? So I could again have O of H if I have S equal to 2. Huh? So therefore the third term is O of H to the power S minus 1. And this is a quick description of the proof of the proposition. Huh? Now, if you analyze this proof, it still works when Q is the characteristic function of a strictly convex domain with smooth boundary, and then all these estimates are valid with S equal to 3/2. Huh? And now I return to our system here. The system 3 is just a rewriting of the original problem. And I'm looking for, so phi j0, so phi 10 is the function 1, phi 20 is 0. And these are the corrections for the exact solutions. And these corrections should solve this inhomogeneous system. And now we had the formula for the inverse of 1 minus k, which was on the diagonal. We had one matrix to the left, which was 1 minus AB inverse, and then 1 minus BA inverse at the other side, and then a matrix with 1 on the diagonal and A and B off the diagonal. So I apply that formula, and then I get the formula for the correction here. And now AB is of norm H to the power S minus 1. So I get, so when I expand this in the Neumann series, I get the identity plus something of operator norm O of H to the power S minus 1. So phi 1 has this approximation in the space I'm interested in. For phi 2, it's very similar, and I'm probably wrong about this factor sigma between focusing and defocusing. I'm not sure that I put the sigma correctly everywhere, but so maybe we can just forget about the sigma and take sigma equal to 1 everywhere. So this still holds when Q is a characteristic function. And then it holds with S equal to 3/2. So actually this term is simpler than this one, because this term involves the inverse of the D operator, or maybe D bar, I forgot, maybe D operator. The other term also, but then comes one more inversion so if this is the inverse of the D operator, this should be the inverse of the D bar operator. So this is a more complicated term that we have not yet analyzed very far, but this one we have analyzed it quite far in the case when omega is a characteristic function. So I will tell you a little about what you get in this. So now I'm looking at the leading correction term, which is this one. Let me go back so just to see. So it's this term here that we should analyze. The analysis of this one will lead to double integrals that has not yet been done. Should work also, hopefully. So what is this? Well, Q is the characteristic function of omega. So, and also F is just 1 over H times the inverse of the D operator. So this H and the 1 over H sitting here, they cancel. And then tau omega hat is just multiplication by this, and I multiply this, the characteristic function of omega, with this function here. And then I invert my D operator, which is same formula as for the D bar operator, except that I have Z bar minus W bar. So here it is, so this is the formula, and I call this expression 1 over 2 pi F bar of Z of K, small f bar. So F is just a complex conjugate of this integral. It's written here. And I want to apply Stokes' formula. So I write the Lebesgue measure as a differential 2 form. And then I have this expression here for Z. And now, so what do we want? So I want to apply Stokes' formula. So I would like this to be the differential of some function. Sorry, I would like to have this 2 form here as the exterior differential of a 1 form. And you try a little, and then you get. So you try this as a primitive form. When I take the exterior differential of this 1 form, I get this, and this is what I wanted, except that I have an additional factor chi bar. So how do I get this? Well, this is just ddw bar acting on this. So ddw bar on this will produce a delta function sitting at the point Z. So it's written here. And when the ddw bar hits this one, I have multiplication by k bar. And this is what I want. So I move this over to the other side. I divide by k bar, and I apply Stokes' formula. So the integral of this over omega is equal to the integral of this thing here over the boundary. So it comes here. And if Z is inside omega, so I integrate over omega, so if Z is inside omega, I get an additional term here. So I write this with the characteristic function of omega times, I have this division by k bar. So I get this expression here as an additional term. Now I want to study this integral further. So you can already see here that this exponent here is purely imaginary. So you have an oscillatory integral on the boundary. So therefore the natural reflex is to try to see if this function here has, so it's e to the power I times thing which is oscillatory. I write it here. And then you look for critical points of this oscillatory function. So I will not write this and therefore you could already do this, you could do stationary phase on this integral in some situations to get an expansion. But we prefer to do the full method of steepest descent. So at least in our first work, we assume the boundary to be real analytic. So I will parameterize the boundary with the positive orientation. So it's written here. Actually, you don't have to look this too much detail. And what I have, and then I recall that this is this is e to the power minus I u naught, where I u naught is given by this expression here. And then so what you find is the following. You take the interior unit normal to the boundary at any point on the boundary. You define the North Pole to be the point where the interior unit normal is equal to a positive multiple of omega, and the South Pole where it's equal to here it's a negative multiple and here it's a positive multiple. Then I will show you a drawing on the next slide. Gamma plus is the boundary segment from the South Pole to the North Pole when you go around the boundary with a positive orientation. And gamma minus is the open boundary segment where you go from the North Pole to the South Pole on the other side of the obstacle. And then what you check is that these poles are precisely the critical points of the phase function I have along the boundary. And more precise, and they are non-degenerate critical points. And gamma plus is the set of is precisely the set of gamma t, where the derivative of minus u naught is strictly positive, and gamma minus is the set of points where the derivative of minus u naught is strictly positive. Actually, maybe we should have switched here the definition so that u naught change sign, but at least we have some, hopefully not too many sign errors in the computations. So now I take the holomorphic extension of u naught to some neighborhood of the boundary, because I assume that the boundary of omega, so omega sits inside the black curve here. The black curve is the boundary. Since this is real analytic, I have a holomorphic extension of u naught to neighborhood. And since minus u naught has a positive derivative here, the extension will have a positive imaginary part if I go in this direction here. So in the blue region, the minus the imaginary part is positive. Near gamma minus, I have the opposite phenomenon. So therefore, what I want to do is I want to gain exponential decay. So I want I want e to the power minus I u naught to become exponentially small. So therefore, I want to deform gamma inwards here and outwards here. And here, at least to start with, I choose 45-degree angles. And then you are precisely in a steepest descent situation. Okay, and therefore there was an integral formula so let's have a look at the integral formula. I go back to 12. Here is so this is the function I want to study. It's the characteristic function times something, and then this integral here. And now I replace the boundary of omega with the integral over gamma. Then if my deformation sweeps over, if my pole Z is inside, is swept over by the deformation, then I have to add some residue terms. So, and therefore I get, so when I replace d omega with this one, I have this new term here, but then I have to add residue terms. If the pole sits in, or if Z sits in omega minus, I have to add this thing, this residue term times this factor here. If it sits on the other side, because of the orientations, you get different sign, I get this thing here. And this is the term we already had. And then the last step in this analysis is then to analyze this function as precisely as possible. I will not give a full account for this. Just to say that, so I have this integral here. Now, suppose that if Z is not very close to the poles, then gamma goes away from the boundary, away from the poles. And if Z, by accident, if Z sits close to the deformed, to the deformed gamma, then I can deform gamma a little more, so that avoid a neighborhood of Z. So therefore, by modifying gamma, I have I can really apply the method of steepest descent, and I have the typical stationary phase expansion here. So what did I want to say about this? Well, then you can look at the leading order terms here. So T plus and T minus, they are the times for which I go through the poles. So these Hessians here, they are non-degenerate, and it's independent of Z. This one also is just a complex number. So this is this factor here, but in U I have a factor K. So this behaves like 1 over K to the power 1/2. So the leading term, if Z does not become large, each term here behaves like 1 over K to the power 1/2. And then I have a remainder term, as in the stationary phase formula. I gain 1 more power of K, so I get K to the power minus 3/2. Then I can, if Z becomes large, this behaves like 1 over Z. And this I keep also for the remainder term, because it's just the amplitude which becomes small when Z goes to infinity. And this can be pushed now when Z comes close to the poles. This is still valid as long as I avoid the neighborhood of the size 1 over square root of K, roughly. And then this expansion, so if I'm very close to the North Pole, this expansion loses its sense when I get inside the K to the power 1 minus half neighborhood. But this can still be, this region can also be studied. But then we need a special function. So I don't know if this is a classical special function. Maybe it can be reduced to some. So I introduce this special function here. So it's just that I take a contour, an unbounded contour. I go from infinity to infinity. I integrate this Gaussian function times 1 over Z tilde minus W tilde. And actually there are two functions, because you have to, of course, you choose your contour so that you go from a deep valley of this function where its expansion is small. Then you have to go up to the pass, and then you go down in the opposite valley. And then there are still two functions, because if Z tilde now starts to move, you have to decide if you want to pass to the right or to the left of Z tilde. But apart from that, this is this function is, so there are two functions and they do not depend on any particular choice of contour here. So I can use this function to give an approximation. So when the term gets wrong, goes wrong near W plus, I have another expression using this, and I still have a good approximation. So that's somehow the main result is, which I did not write down, is that, so how much time do I have? I have so the main result is that I have these approximations, and then I have quite a detailed study of this term here. Namely, it's equal to the complex conjugate of a function f, for which I have a first development of this form, and then another development here, and finally I get f of this form, and then in all regions I have an asymptotic approximation for this function capital of f. Now this is the leading term in the correction of the function phi2. The correction for the function phi1, we have not yet done it because there will be probably, this cannot be avoided, I think, that we will get double integrals. So we have this twice here. No? So, but there is a corollary which uses much less of this detailed result, namely the leading correction to phi2 has this expansion in the weighted L2 space. So you see that the leading term here behaves like 1 over k. And then you have remainders which behave like h to the power 3/2 times half the power of the logarithm. And I think this is a satisfactory result. This is not, this one looks great also, I think, but I forgot now, but I think we can actually, you can apply this analysis once more to this expression here. You get, again, you can get the characteristic function, but I'm not so sure. But if, so this one looks nice also, it's of the order of 1. Sorry, it's of the order of 1 over, it's of the order of h, because in E I have a 1 over h, so it's 1 over k. But so it looks bigger than this term. But so one of the motivations for our study is a certain reflection coefficient, which is the Fourier transform of phi1 multiplied by the characteristic function of omega. And when you look at this Fourier transform, unfortunately, the Fourier transform of the characteristic function of omega decays like h to the power 3/2 also. So when you do that, this term is not better than this one. So there can be cancellation. So this is still something which remains to be done. Huh? So I will end by showing some numerical calculations. Huh? So this first picture here is the solution phi2 to our system. And it's multiplied by k. And you see that, so if you look at the leading asymptotics in terms of sup norms, it's not so clear. But if you allow that you look in L2 norms, then really the bulk here sits at the same level, I would say, huh? times 1 over k. Huh? Then I have, so then I look and then here is a picture for the correction. So this is, the remainder term in the formula. Let me go back. Is a numerical picture of this remainder term here. Huh? Sorry, here. And then I'm not sure that if this, I don't think this is h to the power minus 3/2, but it could be a better power of h. I'm not sure about that. And you can, and then there is another difference here. You can see a difference. Let me look at phi 2. You see here. So this is the case. Omega is the disk. Huh? So there are 2 parts. So here you see the poles. Huh? So I have not checked it, but I'm pretty sure that what you see here, that I believe this is the North Pole. And this is the South Pole. So therefore, this is gamma plus, because if you look at, and you see it's not the same, here it's much larger on this side than on that side. Huh? And there will be a similar picture for phi 1, and the explanation is that, now I'm a little lost here. Now I have to look at I look at this formula. So this function here is equal to this function on the boundary. So when you so when I'm on the gamma, near gamma plus, this term comes with a negative sign, which is opposite to that. So near gamma plus, the solution should be smaller. So in both cases, the presence of these terms takes away the jump discontinuity here, but this term is even better because it goes inside and takes away the contribution from the characteristic function near the boundary. So then the last picture is phi 1, and this is an additional correction term that my co-authors have added. So I haven't fully understood this. But again, you see a sharp difference between the 2 parts of the boundary here. Huh? So this should be, in my opinion, should be gamma minus, and this is gamma plus. This should be gamma plus. So this is the South Pole, and this is the North Pole. Huh? Okay, so thank you for your attention. Huh?
Thank you very much for the very nice talk. Thank you very much. Are there any questions or comments? Please unmute yourself. Are there any questions or comments, please? Are there any further questions or comments?
It was a great talk.
Thank you.
Very, very interesting talk. Yeah. Maybe has applications to electrical impedance tomography. No, you had to look at the D-bar system there. There is a D-bar D system for the conductivity problem.
Yes.
Maybe this has implications for that. One has to look at it.
Okay.
Very interesting talk.
So we will continue on this and look at many more cases. So I think my co-authors insist very much on having the reflection coefficient. It's I think important in the approach in the inverse scattering approach to the Davis-Stewartson 2 equation. So that's probably the next main question, is to refine the study of phi 1 to get the reflection coefficient. And another much smaller problem, which I'm pretty sure will work, is to remove the assumption that the boundary is real analytic.
Right, and that looks plausible.
Mm.
Great talk.
Okay, I also got a question in chat from the audience. So the question is, can we handle the star-shaped domain?
Can we?
Handle star-shaped domain.
What domain?
Star-shaped.
Star-shaped. With singularities then, or?
There is no comments.
A star-shaped domain which is not necessarily strictly convex, huh?
I don't know.
Then you will run into some new difficulties here, because if I apply the method here, you will not always have non-degenerate critical points in that case, I think. Huh? So what happens here, if I take a general boundary, smooth boundary, and apply this method, then presumably for many values of k, so there was the vector omega, which depends on k. For many vectors k, I can do things with a stationary phase, and it should work out fine. But then there will be some directions where it breaks down. Huh? But I was thinking that that's another thing we could do, is to have, as I said in the beginning, I could have strictly convex domains with strictly convex holes sitting inside. Huh? I don't know if that could be of interest for in tomography, because then you just then you have more boundaries. You have, but each boundary component should work the same way, I think. But for star-shaped, I don't know.
Thank you very much. Thank you very much.
One more question. And how low do you think you can go on the regularity of the boundary?
I'm not. This is not. I don't know. I know that, for instance, the work of Perry, and also and especially and the work of Nachman, Regev, and Tataro goes much longer, go much further. It has just L2. Huh? But I suppose that for when you are interested in, when you want to study the asymptotics, then I think you need more regularity if you want to do something, because there is you have some microlocal analysis. You need to do some kind of cutoffs in phase space. Huh? So if the Q is too wild, I don't know what will happen.
Okay, thank you. Are there any further questions or comments? Okay, if not, let us thank the speaker again. Thank you very much, everyone, for coming. Thank you very much.
Thank you.